my dear students, this is Dr. Mocha, and today we'll be talking about effective forces. In this lesson, we're going to discuss what forces are, what they can do to an object. We're going to also talk about the sketching and plotting and interpreting of a load extension graph for elastic solids. And we're going to talk about what are resultant forces, or the resultant of two or more forces, and whether it's going to affect the motion of my object or not. And finally, we're going to explain what friction is for solids and for liquid or gas as drag. Let's start by the main thing, which is, what is a force? A force is a push or a pull, which can cause an object to do a couple of things, such as speed up, accelerate, change velocity, change direction, change shape, size, or even rotate. When a force is applied to a solid object, it can do one of three things. Either it will make it stretch, which is known as tension, or compress, which is known as compression, or it can cause it to bend or deform. Now, I can make the object bend, but if I let go of my force, it will go back to its original shape. However, if I bend it with a lot of force, I can cause it to deform. What's the meaning of deform? It means that if I don't apply that force anymore, it's not going to go back to its original shape. Okay? So these changes are known as temporary, which is known as elastic, or permanent, or in other words, plastic. Now, let's look at the load extension graph. Here I have a graph with force versus extension. Pay very good attention, because once I'm done with this, I'll show you another graph that's very, very important and very, very similar that may come to you when assessed about this topic. So just imagine this with me. If you have a spring and this spring does not have a load, so this is my original length. Is there any extension? No. So we start at 0. Now, if I do apply a load, then this spring will start going down. It could, for example, reach all the way here if I'm applying load. Load, by the way, means something that has a mass or a force. So when I apply load, it will go a little bit down. So this is what we call, this length is what we call an extension. Okay? So the more I apply force, of course, what's going to happen? The spring is going to extend further down. So this is what we call Hooke's law, that the further or the more I apply a force, the more my spring is going to extend. But of course, everything has a limit. So as long as there is a linear relationship between force and extension, then this is known as Hooke's law. Now, the second this linear relationship ends, which means that as force increases, extension increases linearly, proportionally. Once this ends, they are no longer increasing at the same rate. We call this point where that linear relationship ends as limit of proportionality. After that, what's happening? I'm giving the spring a little bit more force than the limit of proportionality. So what's happening? The spring is still going down, and when I remove the load, it still goes back, but it doesn't go all the way back to its original shape. So here, it is not applying Hooke's law anymore. It is a little bit elastic, and that's why it's still within the elastic limit. After that, if I increase it a bit further, this is when the elasticity of my spring is no longer working, and this is what we call a plastic deformation. So again, to a certain force, I have Hooke's law applied, and the more I apply the force, the more the spring extends. If I remove the force, the spring goes back to its original shape, up to the limit of proportionality. If I increase the force more than that, the spring will go down, and if I remove my load, it will go, but it will not go all the way back to its place. So here it's a little bit elastic, but it's no longer Hooke's law because they're not directly proportional. After that, if I increase the force even further, this is where I reach my yield point, where I reach my deformation of the spring. So in this case, the load, which is the force, applied to the material, and the unit of force is, of course, newtons. Extension, x, which is the increase in length compared to the original length, and this is in meters or centimeters. So if you have a question that's asking, a load extension graph shows a straight line from 0 to 4 Newton, and then curves, no longer a straight line, from 4 Newton onward, what's the limit of proportionality? Take a minute, think about it, pause the video, and then unpause to see the answer. The correct answer is 4 Newton. Now, if I want to check something which is known as the spring constant. Spring constant is the relationship between the force and the extension during Hooke's law. So spring constant only applies to Hooke's law. The spring constant has the letter K representing it. So spring constant, we said it only applies to which law? Only in Hooke's law. Can I apply it after that? No. Okay, what's the law? It says that the spring constant is equal to the force over the extension, where K is the spring constant, F is the force, and X is the extension. If my force is in newtons and my extension is in meter, then my spring constant will be in Newton per meter. If my force is in Newton, of course, but my extension is in centimeters, then spring constant will have the unit Newton per centimeter. Okay? Clear? So what is spring constant again? It's the relationship between force and extension during Hooke's law region only. After that, we cannot apply this law of spring constant to the region after the limit of proportionality. Okay, so let's move to example 2. A spring is stretched by 0.04 meters when a 2 Newton load is applied within the linear region. What is the spring constant? Pause the video, try it on your own, and then unpause to check the answer. In the question, they gave me the extension to be 0.04 meter. So that's my x. And the load to be 2 newtons. So that's my F. So what's the spring constant? We already said that K is equal to F over X, just 2 over 0.04, giving me 15 newtons per meters. Okay. Next, we need to talk about Newton's first law of motion. Newton's first law is very easy. Imagine if you have a football and you put it on the floor and there was absolutely nothing coming near it for the next 100 years. No one pushed it, there was no air, no earthquake, nothing came near it at all. After 100 years, you come back to that place. You'll find that the ball is exactly where you put it, because no external or resultant force was applied to the football. So it will stay exactly where it is. How about if you go to space, where there's absolutely no external force? There's no gravity, there's no air resistance, water resistance, nothing. And you throw a ball in space. It will keep going at the same speed, in the same direction, forever and ever and ever, as long as no resultant force acts on it. So we took two cases. If something is at rest, it will stay at rest unless a resultant force acts on it. And if something is in motion with no forces, no external forces, then it will stay in motion in the same direction and speed unless a resultant force acts on it. This is Newton's first law of motion. So if the resultant force is 0, an object at rest will stay at rest, and an object in motion continues to move with constant velocity in a straight line. So what do you mean by resultant force is 0? Resultant force is nothing but the difference of forces acting in opposite direction, or the addition of forces acting in the same direction. So for example, if I'm looking at the example of the object that is sitting on a table with its weight and upward force. If I have the upward force as 3 Newton and the weight is 10 Newtons, then what is my resultant force and the direction? The resultant force will be, if they are in opposite direction, I will subtract. Same direction, I will add. So they're in opposite directions. So therefore, my resultant force will be 7 Newton. And who's winning? Who's the bigger number? 10, which is downwards. So this will be my direction, downwards. Okay? What if I have another force helping this guy of, let's say, 7 Newtons? And I ask you now about the resultant force. You're going to say, oh, I have 7 Newton and 3 Newton, both of them pointing up. So that's 7 plus 3. We said in the same direction, we add. 10 Newtons pointing down, so that's 10 down there. So I have 10 up, 10 down. So is there any resultant force? Nope. I have 10 Newton up, 10 Newtons down. And when I subtract, because they are in opposite directions, I'll get my resultant force as 0. And that's what they mean by if the resultant force is 0. Okay? So they don't mean that there is absolutely no force. They mean that the forces acting on it are equal. Okay, Newton's second law is also another easy law. What did Newton say in his second law? He said that if an object is moving, the object's motion will depend on two things. The acceleration of an object will depend on force and mass. If the object has a larger mass, it's heavier, will it move faster or slower? Will it accelerate easily or not? If the object has a bigger mass, it will not easily accelerate, right? It's heavier, so it will not move faster easily. So that means that if the mass increases, the acceleration will decrease. So the heavier something is, the less it will accelerate. The lighter something is, the more it will accelerate. What about the force? If I hit a ball slowly with very little force, it will accelerate less. If I hit it with a very large force, it will accelerate more, especially that it's the same ball with the same mass. Okay, so if I give the same ball more force, then it will accelerate more. If I give it less force, it will accelerate less. So this is what they mean when they say the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass. So force increase, acceleration increase. Mass increase, acceleration decrease. And this takes me to my relationship that force is equal to mass times acceleration. I know that some of my students like the magic triangle, so I'll write it for you here. Force, mass, acceleration. If I want the force, I'll multiply mass times acceleration. If I want the mass, I'll do force divided by acceleration. If I want acceleration, I'll do force divided by mass. Okay. In this example, since I'm talking about newtons, then my mass must be in kilograms. Miss, what if I get it in grams? Nope, convert it first before you answer. Acceleration is in meters per second squared, and the direction of acceleration is of course like we said a few minutes ago, in the same direction of the net force. Try this example, pause the video, and unpause when you're done. A 5 Newton force pulls a crate to the right and another 5 Newton force resists to the left. What's the resultant force? So we have 5 newtons to the right. I like marking when I'm answering. It makes me see numbers clearly and the directions if there are any. 5 newtons to the left. They want the resultant force and motion of the object. So they wanted two things, not one. 5 newtons to the right, 5 newtons to the left. So my resultant force will be 0 Newton. So will there be any motion? Nope. Another example, pause the video, unpause when you're done. A 10 Newton force pulls a box to the right, while 4 Newton friction force resists to the left. What's the resultant force? Again, 10 Newton right, 4 Newton left. So my resultant force, since they're in opposite directions, I'm going to add or subtract? Subtract, of course. So 10 newtons minus 4 newtons is 6 newtons. Who wins? Which has a larger force? The right. So it's 6 newtons to the right. Third example, pause the video, try it on your own, and unpause. A car of mass 800 kilograms has a resultant force 1,600 newtons forward. What is the acceleration? So we're going to use the same equation we took, which is force is equal to mass times acceleration. But remember, check your units before you answer. I told you if it's in newtons, mass must be in kilograms. So we're good to go. So force equals mass times acceleration. Rearrange the equation where mass goes down here because I want acceleration on its own. So acceleration will be force over mass, which will give me 2 meters per second squared. Next topic, friction in solids. We have 3 kinds of friction in solids. We have static friction. Static friction means that I am applying a force, but the object is not moving. This is known as static friction. The second kind of force is sliding friction. This happens when I have an object that has its surface area across the surface area of the ground or the floor or the table. So this is a sliding friction or sliding motion. Then we have the rolling friction when I have something like a cylinder, and in that case it does a rolling motion, which is known as rolling friction. Now, of course, which one will give me the most friction of them all? Static friction will be the most friction, and then followed by sliding friction, followed by rolling friction since it has the least surface area on the ground. So overall, solid friction is a force that resists the motion of one solid surface sliding or even trying to slide over another. It's parallel to the surface in contact and in the opposite direction to motion or attempted motion. So obviously it slows it down. It causes heat due to the energy being converted into thermal energy. Particles vibrate more with heat. And the rougher the surface is, the more there will be friction. Just imagine if you're trying to slide with your feet on ice versus on grass versus on wood versus on concrete. The rougher the surface is, the more you'll feel the heat on your feet. That's because the rougher the surface, the more the friction. In so many places such as factories, they have machinery that requires that a lot of friction can occur, and this causes a lot of problems because with time, those machineries are going to break. So what happens is that they apply lubricants such as oil or grease so that it would reduce the friction a bit, making the surface of my machine a little bit smoother and slippery to lessen the friction that is happening. Here's an example. Pause the video, try it on your own and unpause please. A wooden block is pushed but does not move. This is very important. I did apply force, but it did not move. What force prevents the motion from the forces that we just talked about? Static friction. As long as the applied force is less than the maximum static friction, the block will not move. It will remain stationary. When you rub your hands together quickly, they feel warm. What causes the heating? This one's easy. Friction, because it converts the mechanical energy into thermal energy, and hence you feel the frictional heat raising the temperature of your skin. Next, we want to talk about friction in liquids. Now, bear in mind that both liquid and gas, their friction is known as drag. Of course, sometimes it's known as air resistance or water resistance, but the more general term is drag. So, drag is a type of frictional force that acts on an object moving through a fluid. And when we say fluid, we always mean liquid or gas. It doesn't only mean liquid. And here in a liquid, this is called viscous drag or fluid resistance. Why viscous? You'll know in a second. Drag always acts in the opposite direction, just like friction, to the object's motion. Now, what causes drag? The cause of drag is that as an object moves through a liquid, it must push liquid particles out of the way, which slows down the object due to the resistance of those liquid particles. Okay, what can make my drag a bit more or a bit less? This water resistance, what can make it more or less? Well, the faster the object is, the more the water resistance or the drag is. Because it's trying to resist you a bit more, the faster you're trying to move. The viscosity of the liquid is very important. Imagine swimming in a river versus seawater. The thicker the liquid is, the harder it is to move, right? Why is that? Because thicker liquids like oil cause more drag than thinner ones like water. Last but not least, shape and surface area. Imagine dolphins, imagine swimmers wearing the head caps, imagine the way boats are shaped. Whenever I have a streamlined shape, like a fish, what do I mean by streamlined? It means that when the water particles are coming to resist the motion of the fish, they can't resist it much because there isn't much surface area to go against. So this is what we call a streamlined body. Versus something like that, then it will have a lot to resist, right? So a streamlined body will make the drag less. Remember, in liquids, drag increases with speed, but not always linearly. That means they don't have a linear relationship like what we say in this lesson that has a linear relationship. Hooke's law, right? Okay. Here's an example. Pause the video, try it on your own, and then unpause. A small ball is dropped into a beaker full of oil. As it falls, it slows down and then moves at a constant speed. Why? At first, this is always relevant to the word terminal velocity, especially when they say the word constant speed. In the beginning, the weight is more than the drag. So what happens? It accelerates. After a while, as the speed increases, what's happening? The weight becomes equal to the drag. So I no longer have acceleration. What do I have? Constant speed, which is also known as terminal velocity. Okay, this is a 2-marker and sometimes a 3-marker question. So step number 1, the weight was more than the drag, whether it's air resistance or water resistance. I'm talking about generally. Second step, as the speed increases, the weight becomes equal to the drag, which results in constant speed, which is terminal velocity. Here's another example. 2 identical marbles are dropped, one in water, one in honey, which experiences more drag. Here we're talking about viscosity. So honey has higher viscosity than water, so it produces more resistance to motion. The marble in honey experiences greater drag and hence it falls more slowly. Finally, let's talk about dragging gas. You need to know, of course, the names of the forces. Some of my students asked me, okay, miss, can we have a different name other than lift, such as air resistance? I was like, no. Air resistance resists your direction of motion. So since your motion is to the front, then air resistance will be to your back. However, another example, like the person falling with a parachute, okay? This person is moving down due to his weight, gravity. So then air resistance will be moving up. So air resistance always resists your motion. It's opposite to your motion. So dragging gas, when an object moves through a gas like air, it experiences a frictional force known as air resistance or drag, which acts in the opposite direction to the motion of the object, converting some of its kinetic energy into heat, and it's a form of fluid friction. As we said, fluid is for liquid or gas. What affects the air resistance or the drag? Also the speed of the object. Faster objects have greater air resistance. If they have a streamlined shape, then the air resistance will be less. If they have their surface area is larger, then it will have more drag, like parachutes. And density of air, of course. If it's more dense, then there will be more drag. Here's an example. You may try it, pause the video, and then unpause to check your answer. A skydiver jumps out of a plane and starts falling. How does air resistance affect their motion? Same thing. We're going to have the gravity causing the skydiver to accelerate downwards. So therefore, we have more acceleration than the air resistance. Right? Because due to gravity. The acceleration here is due to gravity since something is falling. Okay? And then after a while, what's happening? As speed increases, the air resistance becomes more, so the acceleration becomes equal to the air resistance. And we said when they become equal, two things happen. Constant speed, terminal velocity. All right? Here's another example. Why are sports cars designed with a curved low body? Just said it. Because that would give them a streamlined shape, which will reduce air resistance, allowing them to move faster, and this improves two things: fuel efficiency, and they'd reach top speed. We also have another example. You drop a flat sheet of paper and a crumpled paper. So we have a flat sheet, more surface area, crumpled sheet, from the same height. So I have no problem with the height here. Which hits the ground first? Here we're talking about surface area. The crumpled paper ball has less surface area, so less air resistance. So it accelerates faster and hits the ground before the flat sheet. Okay, let's move on to effect of a resultant force on an object. A resultant force is a single force that has the same effect as all the forces acting on an object. When there is a non-zero resultant force, that means that the resultant force has a value, then the object's velocity changes. This change in velocity can occur in two ways, causing acceleration or deceleration. If I change the object's speed, then I change the velocity. If I change the object's direction, then I change the velocity. Here's an example. A car is moving at 10 meters per second. The driver presses the accelerator and the engine applies a forward force larger than the resistive force. So my forward force is larger than the resistive force. And it was already moving at 10 meters per second. What's going to happen? Since the forward force is larger, then it will keep moving forward. So the car is accelerating, meaning the speed is increasing in the same direction, and this improves fuel efficiency and reaching top speed. A ball on a string is swung in a circle, okay? The tension in the string pulls towards the center. So what effect does this have on the ball? If I'm applying more tension, so I'm giving more force, I'm pulling on the string more, tension means pulling on the string more, then what's going to happen to the ball that's going around in circles? It's going to start to decrease its radius. So the tension provides a resultant force towards the center of the circle. This causes the ball to change direction continuously, keeping it in circular motion. The speed may remain constant, but of course, since it's going in a circle, it's changing its direction. So speed is constant, but velocity isn't, because the direction is changing. A cyclist is moving forward, but friction and air resistance become greater than the forward force. What is the effect? The cyclist is moving forward, but friction and air resistance are more. So is he going to keep moving forward? Actually, he will start slowing down because the resistance force is more, so it will slow him down, deceleration. Thank you for the lesson, and if you have any questions, please write them in the comments, and can't wait to see you our next session. Have a good day.